Hello everyone and welcome to my talk on large deviations for Lacanary sums. We start by defining a large deviation principle in R. For this we consider a function I mapping from R to the interval 0 infinity, and we call this function I a good rate function, a GRF, if all level sets, so all sets of this form are compact in R. And we note that the function I is allowed to take the value plus infinity, but at least there has to be one value where I is finite, so it is not allowed that I is constantly plus infinity. Then we can define LDP, so for a sequence xn of real valued random variables, we say that xn satisfies an LDP, a large deviation principle, if there exists a good rate function I mapping from R to 0 infinity, such that both those inequalities are fulfilled. So let us go through the first one. Here we have that for all open sets O in R, we need that minus the infimum of x in O of I of x is smaller or equal than the lim inf as n goes to infinity of 1 over n times log of the probability of xn in O. And the other inequality works similar. Here we consider closed sets A in R. Maybe one might ask the question, what does this have to do with large deviations? So we consider this typical situation where xn is the empirical mean of IID random variable set. And then we know that xn almost surely converges to the expectation of set 1. As n goes to infinity, and then consider the situation when A is a closed set which does not contain the expectation of set 1. Then we know that this probability, so the probability of xn in A, tends to 0 as n goes to infinity, and so the LDP describes this decay to 0 as n goes to infinity. So it describes this rare event, this large deviation. So we come to Lacanary sums, where we need basically two ingredients. First of all, we need a measurable function f mapping from R to R, which is one periodic, so it has a period of length 1. And then we need a sequence of natural numbers ak tending to infinity. And then we can define this quantity here. So we define Sn as the sum of k equal 1 to n of f of ak times u, where u is a uniform distribution on the interval 0, 1. And this sum Sn is called a Lacanary sum. So the ingredients of such a Lacanary sum, again, are the function f and the sequence ak. And then we are interested in the asymptotic behavior of Sn as n goes to infinity. And on this slide, we have a few interesting results from the 20th century. So first, we have the strong law of large numbers for integrable functions f and for the sequence ak equal to 2 to the power of k. We have that Sn divided by n almost surely converges to the integral from 0 to 1 of f of t dt. Then a few years later, Marcatz proved the central limit theorem for certain Hölder continuous functions f, and again for the sequence ak equal to 2 to the power of k, where we have that Sn divided by sigma times the square root of n converges in distribution to the standard normal distribution. And note that this sigma here, it is not the same as the variance, it is slightly different, but the technical details are not so interesting in this point. And then a few years later, Salem and Zygmunt proved the law of the iterated logarithm in case of the cosine function. So it turned out that those Lacanary sums Sn, they show the same behavior as sums of IID random variables, even if the summands of Sn are not identically distributed, nor are they independent, since they are connected to each other by the same random variable u. So one might ask the question, what about large deviations? So does Sn satisfy a large deviation principle? And this question was approached in 2020 by Eistleitner, Gantert, Kabluchko, Prochnow, and Ramanan. One year later, so in 2021, we managed to generalize one of their results. So for this, we consider the Legendre transform. So for a convex function lambda mapping from R to R, we define the Legendre transform lambda star as the supremum. So lambda star of x is the supremum over t in R of x of t minus lambda t. And then we have the following theorem. For a lacunary sequence AK with large gaps, so the quotient of AK plus 1 divided by AK tends to infinity as K goes to infinity. We have that for one periodic and continuous function f, we have that Sn divided by n, so the lacunary sum Sn associated to the function f and this sequence satisfies an LDB with good rate function lambda star, where lambda is given as this cumulant generating function here. So we have an LDB for Sn divided by n, and the good rate function is the Legendre transform of this function lambda. And actually this is quite nice. So for those of you who are familiar with large deviations, you know that the good rate function does not get more explicit than this. So it is quite nice to be able to compute this cumulant generating function explicitly. Okay, then maybe a little sketch of the proof. So I mentioned that the sequence Sn consists of dependent components. So one needs to use the theorem of Gertner-Ellis to prove the LDB. So the other techniques, for example, the contraction principle, are not so, it's not clear how they would be applicable in this situation. And the theorem of Gertner-Ellis works fine here. And then second, we note that such a continuous and periodic function f can be approximated uniformly by a sequence of trigonometric polynomials fm by the approximation theorem of Weierstrass. And then for such a trigonometric polynomial fm, one can prove the LDB more or less straightforward modulo some technicalities. So now one might ask the question, what about the other cases? So what about the situation when AK is a geometric sequence? So for example, the sequence AK equal to 2 to the power of k. Then one is still able to prove the existence of an LDB for arbitrary continuous and periodic functions f. But in this case, the good rate function cannot be computed explicitly. Only for certain cases of functions f, but in general, the good rate function cannot be computed explicitly. Thank you for your attention.